part A, we can set up the diagram. And we have this piece of wood. This would be the density, or rather the pressure of the air. This would be oil, this would be water, and this would be wood. We know that essentially this distance here is 1.50 centimeters. We know that this distance here is 8.50 centimeters. And we know that this distance here is 1.50 centimeters. So we can then say that the gauge pressure is going to be equal to the density times the density times h. We can say the upper face is 1.50 centimeters below the top of the oil. So we can say that then the difference in pressure would be equaling the density of the oil multiplied by 9.80 meters per second squared, multiplied by here 0.0150 meters. And so the difference in pressure would be equal to 116 pascals. This would be our answer for part A. For part B, at the interface, we can say that the pressure at the interface would be equaling the pressure of the air plus the pressure of the oil times G multiplied by 0.100 meters. And so we can say that then the lower face of the block is 1.50 centimeters below the interface. So the pressure at 1.50 centimeters below the interface, we'll call that P. This is going to be equal to the pressure of the interface, rather at the interface, plus the density of water, rho, multiplied by G, multiplied by 0.0150 meters. And I just noticed that this looks like a pressure of the oil. This is specifically rho, the density of the oil. My apologies. We're going to combine these two equations, and we find that the pressure below the interface minus the pressure of the air would be equal to the density of the oil multiplied by G multiplied by 0.100 meters. This would be plus the density of the water times G multiplied by 0.0150 meters. And we can solve. This would be equal to 790 kilograms per cubic meter multiplied by 9.8 meters per second squared times 0.100 meters plus the density of the water, in this case 1,000 kilograms per cubic meter multiplied by 9.8 meters per second squared multiplied by 0.0150 meters. And we find that the pressure below the interface, or the gauge pressure, 1.50 centimeters below the interface would be equaling 921 pascals. This would be your answer for part B. Now for part C, we need to consider this on the block. The area face of the block would be equaling 0.100 meters. Quantity squared, this is equaling 0.0100 meters squared. We're going to let absolute pressure at the top face, PT, equaling absolute pressure at top face. And we're going to say that the pressure at the bottom face, P sub B, this would be absolute pressure at bottom face. We can say that then in the pressure equaling the pressure P, the gauge pressure essentially, or the absolute pressure below the interface equaling the force divided by the area, we can use these pressures calculate the force exerted by the fluids at the top and bottom of the block. We can then say that we can draw a small free body diagram. Going straight up would be P sub B times A. Going straight down would be P sub T times A. And then going straight down would, of course, be the weight of the block. And so we can apply Newton's second law in y direction. We can say then the pressure at the bottom, the absolute pressure at bottom face times the area minus the pressure at the top face times the area minus mg. This would be equal to 0. And so we see that the absolute pressure at the bottom face minus the absolute pressure at the top face multiplied by the area will be equal to mg. And so we're also going to note that the pressure at the bottom face minus the pressure at the top face will be equal to the pressure at the bottom face minus the pressure of the air minus the pressure at the top face minus the pressure of the air. And so this would be 921 pascals minus 116 pascals. So this is going to be equal to 805 pascals. And that's how we would find the mass and the density, subsequently the density. So the mass would be equaling the difference, P sub B minus P sub T, divided by, or rather multiplied by A divided by G. This is equaling 805 pascals multiplied by 0.0100 meters squared, and then divided by 9.80 meters per second squared. This is equaling 0.821 kilograms. And we then say that the density would be equal to the mass divided by the volume. This is equaling 0.821 kilograms, and then divided by 0.100 meters. Quantity cubed, this is equaling 821 kilograms per cubic meter. This would be our density. That would be our final answer for part C. That is the end of the solution. Thank you for watching.